So in this video we're going to look at convolution. Now, in order to go through it properly, rather than just looking at it in terms of a discrete convolution, which is actually a very simple thing to perform, but I want you actually to understand why we convolve things and why it is the way it is. So I thought what we'll do is we'll just start off with looking at a continuous convolution, and then we'll extend it to the idea of a discrete convolution. So let's have a look at it in Matlab, and this will help provide you with some intuition before we go and start looking at the maths. So you can see the red function has been flipped in the y-axis and it's moving across over the blue function, and we're taking the area between those two functions. And you can see the area is increasing until the red function is completely over the top of the blue function, so that's a maximum area. And then as it moves out, you can see that the area of overlap starts to decrease until eventually the area of overlap goes to 0. Now this new function at the bottom is the convolved function. So let's say we've got these two functions here which we want to convolve. That's h of t and f of t. Now the way we can think about this in a practical sense is that if we think about f of t defining the response of a system to an impulse, so what we do is if we were to put a single little impulse in, then this is the output that we would get out. And then if we think about the h of t as an actual signal, so this is a signal we're going to put into this system, but we can think about this signal here as being made up of an infinite number of little spikes, as I've shown here. That is an infinite number of little impulses. So we can take this function here and we can run it across that function in some manner, and if we were to run it across that function, then we can produce the output to the system. So this is a system, this is the input, and when we convolve them together we're going to get our output. So what we're interested in doing is taking this input and sliding it over this function f of t, and we're interested in combining them and looking at an area of overlap. So what we want to do is see how we can mathematically take this function and slide it over the top of this one, and then generate a combination of the two and then work out what the area is going to be. So let's look and we'll see how we're going to do that. Now the first thing to note is that if this is the input to the system, then we can see that the actual first part of this signal to actually get into the system is not this part here. The first part to get into the system is at t equals 0. So this here is the first part of the signal to get into the system, because in order to get the rest of it in we're going to have to wait. So this is, say, 1 second later that this actual signal goes into the system. So in order to get this part to get in first, we're going to have to flip this entire signal over in the y-axis. So if we had a function h of t, I'll just draw this out roughly here. If we had a function h of t and we wanted to mirror it in the y-axis, then what we do is we form the function h of minus t. And you can see that quite simply. If we went to a value here, somewhere here, and we looked at the height here, h of t, then we want that same height to be at the minus t value. So I would go to minus t, and I would want to get the same height, so I would get a height here. And then similarly with each of these points here, I want this height here to exist over here. So then we would get this here, which in effect would be this function flipped over in the y-axis. So now we know how to flip the value in the axis, the y-axis, but how are we going to produce the sliding? So we want to slide that flipped function over the top of f of t. So mathematically as well, if we had this h of t, in order to slide a function, all we have to do is add on a delay. Now to add on a delay, it would be minus, say, t naught. So h of t minus t naught, it would be like h of t, but it would be delayed by a factor of t naught. So if it's minus t naught, it's going to move to the right. If it had been plus t naught, it would be moving to the left. Again, you can convince yourself of that heuristically just by putting values in, and you can see that the value of the minus t naught will actually move the whole function to the right. So now this is a detail I think that tends to get missed out when you're learning this at first. When we're doing the sliding, we're not sliding the function h of t, we're actually sliding the function h of minus t because it's been flipped. So in order to flip it and produce the sliding, we're going to end up with a function h of, and it would be the minus t, and it's going to be delayed by some factor. So I could call this factor minus t s. S could be for slide. So we're left with that function there. So the actual function we're interested in is going to be h of minus ts. So now we want to take our two functions, that's our f of t, and we want to combine them together. So that's f of t combined with this new function here. So we combine them together simply by multiplying them. So we're going to have this h of minus ts times the f of t. And finally, once we slide the function h of minus ts over the top of our f of t, we want to find and we've combined them together, we want to find the area of overlap. So we find the area by integrating from minus infinity to infinity. But we can see here that we're going to run into some slight problems, and that we're going to have a variable. In this instance here, our variable is going to be our independent variable t, but we're going to have a parameter as well. So by a parameter, what I mean is a value that's going to change. So for example, we're going to slide this function over the top of this one, and then we're going to work out the area, and then we're going to slide it another little bit and work out the area, and then slide it another tiny little bit and work out the area. So we're going to be continually sliding this along in the t-axis. So this other value here, ts, is going to be a parameter. So we're going to have a variable, independent variable t, and we're going to have a parameter of time ts. But we don't call it that, and they don't do it like that. So let me show you how we tend to do it. So what we tend to do is we introduce a whole new independent variable. So rather than have the independent variable as t, we introduce this dummy independent variable, and we call that dummy variable tau. And then we call the actual sliding, so this is the increments that we're adding on, we add on increments of t. So let's go ahead and we'll write that out. So we introduce a whole new dummy variable tau. So the tau replaces the variable t. So instead of having a function h of t and f of t, we have functions h of tau and f of tau. Now we know that the function h of tau, it actually gets flipped in the axis, so that's going to become h of minus tau. But now we know as well that once it gets flipped in the axis, we're actually going to be delaying it by a factor. So now what we say is we're going to be delaying it by a factor of t, and a delay is going to be given by minus t. But still remember here that in this instance here now, tau is our independent variable and the value t acts like a parameter. So that is equivalent to writing h of, and we can do minus this minus and a plus, so that's equivalent to saying h of t minus tau. Now what you have to be careful with, and what tends to happen, people get mixed up with this, is that in this instance here, the value of our tau is actually our independent variable, and the value of our t here is a parameter. But it doesn't kind of look like that because it's actually the value of minus tau. That actually looks like, mathematically, it looks like it's a value of t which is independent, and the tau looks like it's going to be the variable that's going to slide that function to the right, but it isn't. It's actually the other way round about, and it's a very easy mistake to make, and it's something that tends to be brushed over whenever you're first learning it. So I've gone over that little bit in a bit more detail than you maybe normally see. So let's get back on track here. So we're going to have our function h of t minus tau. We're going to multiply it by our function f of tau. And then we're going to integrate from minus infinity to infinity with respect to d tau. So that's in this direction. So this can best be seen if we look at it in 3 dimensions. And then what we can do is we can actually split up our t axis and our tau axis, and you can see the actual connection between the dummy variable tau and our variable t. So we're taking our function here, h of t minus tau, and we're sliding it across this f of tau, and we're integrating from minus infinity to infinity with respect to d tau. So we can see here we've drawn out our tau axis, so that's our tau axis just like the axis here, that's our tau axis. But now we've drawn out our t axis as well, so this is a t axis here, and our g of t is going to be our final convolved function. So what we're going to do is we're sliding this along, but as we're sliding along, what we mean by sliding along is we're adding small factors of t, which is our parameter. So we're adding a small factor of t on here, which in effect is sliding this in this direction, and we're looking at the multiplying the two together, and then we're going to integrate, that is, we're going to find this area. So this is the area here. Now the height of that area, the value of that area there is going to be the height of this function g of t, which is our convolved function. And you can see that we can pick another value for the t, so we can say that's t0, we could call this t1. So this is now been slid further along. So in this instance, this triangle would say have been slid all the way over on to the f of tau. So it means that we've got a maximum area of overlap, so we had a maximum height here. And then you can pick another value for the parameter t and another value, and so on and so forth. Now I've only shown it out in a kind of digital format here just for representation, but of course you're actually sliding it in a continuous manner, and we're going to generate this function here, which is going to be our output, which is our g of t. So I think this 3-dimensional approach shows you the connection between the variable t and the dummy variable tau. So I went over this in a little bit more detail than you would see normally. The reason for doing that is that I've seen people saying, for example, we have a function here h of t and we're delaying it by a factor of tau. Now that isn't actually what's happening if you're maybe being pedantic about it, but what's happening here is we're taking a function h of tau and we're delaying it by a factor of t. So the tau is the independent variable here and the t is the parameter, not the other way round about. So that's us going over that in some detail, and hopefully I've covered and cleared up some misconceptions. So let's go on and we'll have a look at doing the discrete convolution, which is going to be really quite straightforward. So instead of just having the integration here, we're just going to have a summation, so it should only be another couple of minutes to describe that. So let's look at the discrete convolution. So none of this really should be any surprise to you if you've picked up what we did in the last slide. So if we were to take a function h of n, now the square brackets there represent the function's actually a discrete function, and the time axis is actually represented by the index n. So we have our function here h of n, and it's just the same type of function that we've seen in whenever we did the convolution here of a continuous function. So we've just split it into little sections. Okay, so we've got our h of n here, and we're going to be convolving it with another function, our f of n. So our f of n again is just this little discrete function here, and that's just the same as the function that we had up above here. So what we're going to do is we take our h of n and we introduce the dummy variable k, So then we end up with h of k, but then we have to flip it on the axis, so we end up with h of minus k, and then we are going to be adding on our small increments of n, so we have our h of n minus k and our function f of k. So compare that to the one above, and you'll see it's just the same as we've got above, but we've just got different values in here. So then if we're going to convolve these two functions, what we do is we multiply them together. Now instead of integrating, we're going to add them, so we're going to add them from k equals minus infinity to infinity of h of n minus k f of k, and that's going to give us the final output, which is our function g of n. So this here is our discrete convolution, so this is a counterpart to what we did above, so it's a counterpart to this equation here. So we can see here graphically we've split the variables here, so k is our variable that our dummy variable that we've added, and this is the k-axis that's the k-axis along here, and this is the n-axis along here. So whenever we go to do the convolution, we're simply sliding this function along on top, and whenever this part of the function sits on top of that, then we simply multiply these two together. So we multiply the two together, and that's those multiplied together, and then we add everything up from k equals minus infinity to infinity. But you can see here we've only actually got one value here that's sitting on top, so we've only got this one value here. So this height of this value becomes the height of our function g of n. And then when we slide it along to the next point, then this one here is going to sit on top of this one. So that one will multiply that one, will give us this, and this one here is going to sit on top of this one. So those two will multiply together. So now we're going to have 2 here, and we're going to add these two up, and when we add the two up we get the height here of our g of n. And then when we move along to the next point, then this one here goes to the third one along, this one goes to the second, and this one goes to the first. So we end up with the 3 points, and when we add the 3 points we get this one here. And finally when we take the when we move it along to the fourth point here, we're going to have this one goes to this one, that one goes to that goes to this, and this goes to this one here. So we're going to have the 4 points here, so we're going to have a value. And we can continue doing this until eventually this entire function has just moved out. So the very last one we're going to have, this one would be outside, it wouldn't be multiplying anything, that wouldn't be multiplying anything, neither will that, and this one here will sit over the top of this one, and again we'll be back down to just one value here. So we build up this discrete convolution in that manner, and you can see it's actually quite a simple format. So we're going to go through and we'll work through an example just now. So let's look at our discrete convolution in Matlab. We want to convolve these two functions, so there's h of n given by this discrete impulse train here, and f of n given by this discrete impulse train, and we're looking to find h of n convolved with f of n, which will give us our g of n. So our convolution function is g of n equals the sum from k equals minus infinity to infinity of h of n minus k f of k. Now here's the 3 simple lines that we need to put into Matlab. We've got our function h equals, and we can with square brackets we just put what our impulse train is. So it's 0, 1, 1, 1, 0, 0, 0, 0, and the f is 0, 1, 1, 1, 1, 0, 0, 0. In order to convolve it, we simply do the g equals conv h comma f, and that will give us our output. Now I've actually printed it out here. So we've got our input h of n, which is our impulse train 0, 1, 1, 1, 0, 0, 0, 0, and we've got our f of n, which is the other impulse train, and we've got the output here, which is the convolve function. So this is what happens when we run our Matlab code and we plot it out, and this is the convolved function here. So this is the output from Matlab, giving you all of the values here for our final convolution, and this is just what we've got printed out up here for the function g of n. So we just follow our convolution function here. So remember, this is going to be the first part of the signal that's going to come in. So we're going to have our 0 times the 0, which will give us a value of the 0, and then the next one will come in. So we'll have this one will go to this one, and this one will go to that one. So it'll be 0 times 1 will give us a 0, and 1 times 0 will give us a value of 0. And then the third one will come in, so it'll be 1 times 0 will be 0, 1 times 1 will be 1, and then 0 times 1 will be 1. So when we add them all up, we just got the value of 1. And we look at the fourth one coming in, so it'll be 1 times 0 will be 0, 1 times 1 will be 1, 1 times 1 will be 1, and then 0 times 1 will be 0. So when we add all those up, we'll have 1 plus 1. The 1 plus 1 will give us a value of 2, and so on and so forth all the way along until we get our convolved function here, g of n. Now don't take my word for it, write these down and turn that round the opposite way and feed it in and see that you can actually get this function coming out. So that's us finished with convolution. I've left a PDF with a few examples that you can work through in the resources section. I've also left a copy of the Matlab file so that you can run up and create this output of your own in Matlab. So thank you for listening. I'll get you on the next video. Goodbye.